My name is Rishabh and I'm going to talk about the topic water treatment systems. The course title is Engineering Chemistry and I am from CSE AML branch second semester. In this slide, we are going to discuss what is water treatment and why does it exist. Water treatment is the process of removing contaminants, pathogens and undesirable chemicals from water to make it safe for a specific use, drinking, industrial process, agriculture or discharge back into the environment. The need exists because natural water sources, rivers, lakes, groundwater are not inherently safe for human consumption. They contain suspended solids, dissolved minerals, organic matter, bacteria, virus, heavy metals, and increasingly synthetic chemicals like pesticides and microplastic. Without treatment, waterborne diseases like typhoid, hepatitis can be spread towards the population. As spread rapidly, the World Health Organization estimates that unsafe water is responsible for over 1.4 million deaths per year globally. Water treatment is therefore not just an engineering problem, it's a public health necessity and one of the humanity most impactful infrastructure system. On this slide, we are going to study about the global water crisis context. Before diving into how treatment works, it is important to understand the scale of the challenge. Only about 2.5% of earth water is fresh water, and of that, less than 1% is accessible in rivers and lakes. The rest is logged into glaciers or deep underground. Over 2 billion people currently lack access to safely managed drinking water. Rapid urbanization is straining existing treatment infrastructure in developing nations. Climate change is altering precipitation patterns, causing droughts in some regions and flooding, which is overwhelm treatment system. In others, industrial agriculture introduces enormous quantities of nitrates, phosphates, and pesticides in water bodies. Water treatment in engineering is therefore expanding rapidly, moving from simple to towards sophisticated multi-stage system that must handle an increasingly complex cocktail of contaminants. On this slide, I'm going to discuss about the types of water that need treatment. Not all water treatment is the same. The source and intended use define the process entirely. Drinking water treatment, potable water, has standards regulated by bodies like EPA in US or WHO globally. Wastewater treatment handles water that has already been used from households, hospitals, and industries before it's discharged or reused. Industrial water treatment condition water for manufacturing process where mineral content, pH, or biological load could damage equipment or compromise product quality. Stormwater management addresses runoff from rain that carries pollutants from roads, rooftop, and farmland. Blackish water and seawater desalination converts salt water into usable fresh water, growing necessity in arid region. Each category requires a different sequence of treatment steps and different chemical dosing strategies. On this slide, we are going to discuss about the key water quality parameters. Before treating water, you must understand what's in it. Engineers measure a set of standard parameters. Turbidity measures how cloudy the water is, caused by suspended particles and measured in NTU. pH tells you how acidic or basic the water is. Drinking water should be between 6.5 and 8.5. Biochemical oxygen demand BOD measures the amount of dissolved oxygen microorganisms need to break down organic material. High BOD means heavily polluted water. Total dissolved solids TDS is a combined concentration of all dissolved substance. Dissolved oxygen DO level matters for aquatic life and biological treatment process. Coliforms, particularly E. coil, are biological indicator of fecal contamination. Heavy metals like lead, arsenic, and mercury are individual because they are toxic even at very low concentration. In this slide, we are going to study about the stage 1, screening and pre-treatment. The first thing a water treatment plant does is remove large debris. Raw water from a river or a lake enters through intake structures fitted with bar screens, metal grates that catches branches, leaves, fish, and other large objects. After coarse screening, fine screens remove smaller particles. In some plants, micro strainers, rotating drum screens are used. Pre-treatment also includes aerations where water is exposed to air to remove dissolved gases like hydrogen sulfide, which causes the rotten egg smell, and to oxidize iron and manganese so they can be filtered out later. Pre-chlorination is sometimes applied at this stage to begin disinfection and control algae growth. Through this practice is increasingly being replaced due to the formation of disinfection byproducts. In stage 2, coagulation and flocculation. This is one of the most important chemical stages. Water from natural sources contain extremely fine particles, clay, slate, organic matter, and colloidal substances that are so small they stay suspended indefinitely because they carry a negatively electrical charge that keeps them repelling each other. Coagulation involves adding a chemical coagulant, most commonly aluminum sulfate, alum, Al2SO4 thrice, or ferric chloride, FeCl3, that neutralize the negative charge on the particle. Once neutralized, particles can begin to stick together. Flocculation is a gentle, slow mixing stage that follows, during which the neutralized particle collide and aggregate into large clumps called floc. The engineering design of flocculation tanks, the speed of mixing, the paddle geometry, and the residence time directly impacts how well the floc forms and how efficiently it can be removed downstream. On this slide, we are going to discuss about the stage 3, sedimentation and clarification. After flocculation, the water enters sedimentation basins, large clam tanks designed to allow the heavy floc particles to settle to the bottom under gravity. This process is governed by Stokes' law, which describes how settling velocity of a particle depends on its size, density, and viscosity of the water. Larger, denser floc settles faster. The settled material at the bottom is called sludge, and must be periodically removed and processed separately. Modern plants use lamella plate settlers or tube setters, inclined surface inside the tank that dramatically increase the effective settling areas, allowing smaller tanks to achieve the same performance. The clarified water, now significantly cleaner, flows over a wire at the top of the basin and proceeds to filtration. Some advanced plants use dissolved air flotation (DAF) instead of sedimentation. Tiny air bubbles attach to floc and afloat it to the surface of the skimming, which is more effective for low density particles and algae. Stage 5, disinfection. This is the most critical public health step. Even after filtration, water may still contain viruses, bacteria that pass through. Disinfection kills or inactivates these pathogens. Chlorination is most widely used method globally. Chlorine gas Cl2, sodium hypochlorite NaOCl, liquid bleach, or calcium hypochlorite are added to the water. Chlorine works by penetrating microbial cells walls and disrupting metabolism. A key concept is CT value, the product of disinfectant concentration C and the contact time T, which determines the log reduction in pathogens count achieved. The major downside of the chlorination is that chlorine reacts with the natural organic matter to form disinfection byproduct DBS like THMS and haloacetic acids HAAS, which are potentially carcinogenic giardia. This is why many plants use chloramines, ozone O3, or UV radiation as alternatives or supplements. UV disinfection is particularly effective against chlorine-resistant pathogens like Cryptosporidium. Chemical dosing and pH adjustment. Throughout the treatment process, a chemical dosing must be carefully controlled. pH adjustment is critical. If the pH is too low, acidic, the water is corrosive and will leach metals from pipes. If too high, basic, it reduces the disinfection efficiency and can cause mineral scaling. Lime CaOH twice or sodium hydroxide NaOH are used to raise pH. Sulfuric acid H2SO4 and carbon dioxide CO2 are used to lower it. Fluoridation, adding fluoride to the target of about 0.7 mg by L, is practiced in many countries to reduce tooth decay. Corrosion inhibitors like orthophosphate are added to form a protective film inside distribution pipes, preventing lead from leaching into drinking water. which is directly relevant to the flame. All of this chemical addition must be monitored and controlled in real time using automated dosing systems and continuous water quality sensors. Advanced oxidation process (AOP) as water source face increasing contamination from endocrine distributing compounds, pesticides, and industrial chemicals. Conventionally, treatment falls short. Advanced oxidation process (AOPS) are family of techniques that generate extremely reactive hydroxyl radicals (OH), which can break down almost any organic contaminant. Common AOP systems include ozone combined with hydrogen peroxide O3/H2O2, UV combined with hydrogen peroxide UV-H2O2, and photon reaction Fe2 plus H2O2. The hydroxyl radical is a non-selective oxidant. It attacks and degrades the contaminants that chlorine cannot touch, including pharmaceuticals like estrogens from birth control pills and PFAS substances, also known as forever chemicals. They are typically used as polishing steps after the conventional treatment, not as a primary process. In this slide, we are going to discuss about the desalination, converting seawater to drinking water. In water-scarce regions, the Middle East parts of the Australia, coastal California, desalination is increasingly important source of fresh water. There are two main approaches. Reverse osmosis desalination is now the dominant technology globally, having overtaken thermal methods due to dramatic reduction in membrane cost and energy recovery devices. Multi-stage flash MSF distillation heats seawater and condenses the vapor. Essential, the same principle has the natural water cycle, but engineered. Multi-effect distillation (MED) uses a series of chambers at progressively lower pressure to boil water at lower temperature, improving efficiency. The biggest challenges are energy consumption. RO still uses 3 to 4 kilowatts per cubic meters of water produced. Brine disposal. The hypersaline rejects stream harms marine ecosystem if discharged carelessly. In this slide, we are going to discuss about the wastewater treatment, primary and secondary. Wastewater treatment is a mirror of a drinking water treatment but focuses on removing what humans have added to water. Primary treatment is a physical, large settling tanks, remove settable solids and floating greases. Roughly 40 to 60% of suspended solids are removed at this stage. Secondary treatment is biological. It is heart of the process. Microorganisms are used to consume the dissolved organic matter in the wastewater. The most common method is activated sludge process. Wastewater is aerated in large tanks where a diverse microbial community. The activated sludge breaks down the organic compounds. The oxygen supply is one of the largest energy costs of the treatment plant. After biological treatment, the water goes to the secondary clarifiers where the sludge settles out. The settled sludge is partially returned to the aeration tank, returned activated sludge RAS, and a partially removed as waste activated sludge WAS. Sludge treatment and biosolids management. All the solids removed throughout the treatment process accumulate as sludge, a semi-liquid mixture that is itself a significant waste stream requiring management. Raw sludge is first thickened to reduce its volume by removing water using gravity thickeners or centrifuge. It then undergoes anaerobic digestion in large sealed tanks. Anaerobic microorganisms break down organic material in absence of oxygen, producing biogas, a mixture of approximately 60% methane and 40% CO2. This biogas can be captured and used to generate electricity, making water waste treatment plants partial energy producers. After digestion, the stabilized material called biosolids is dewatered using belt filters, presses, or centrifuge. Then either land applied has a soil embedment. It contains nitrogen, phosphorus that benefits crops, insaculated or landfilled. In this slide, we are going to discuss about the water reuse and circular water system. The concept of water reuse, also called as water recycling, is shifting from a last resort to a mainstream engineering strategy. There are several levels. Non-potable reuse uses treated wastewater for irrigation, industrial cooling, and toilet flushing. Application where drinking water quality isn't required. Indirect potable reuse IPR involves discharging highly treated reclaimed water into a river, reservoir, or aquifer where it mixes with natural water before being taken back up by a water treatment plant downstream. A deliberate environmental buffer. Direct portable reuse DPR is a most advanced and controversial treated reclaimed water goes directly into a drinking water supply with an environmental buffer. Singapore, Any Waters and Nabibas in Windhoek are famous examples of it. The future of water treatment engineering. The future of this field is shaped by three pressures: climate change, population growth, and tightening regulation on contaminant level. Engineering will increasingly design energy neutral or energy positive plants using biogas from sludge digestion, solar and wind power, and energy recovery from osmotic pressure differences to power operation. Resource recovery will reframe water waste plants as water resource recovery facilities, recovering not just water but nutrition, energy, and even valuable metal. Decentralized treatment, a small scale system embedded in buildings or neighborhoods, will supplement centralized infrastructure, particularly useful for rapidly growing urban areas in developing world. Nature based solutions like constrained wetlands and managed aquifer recharge will integrate with engineered system for cost effective treatment at scale. Thank you.